General requirements for selection of instruments. Selection of instruments. The selection of an instrument for a specific application involves an iterative process conducted jointly by a process technologist and an instrument engineer. This process should be documented for auditing purposes and future reference. Steps for instrument selection. 1. Identify operating cases. Consider all operating scenarios such as normal operation at minimum, normal, and maximum flow, alternative operating modes, startup, commissioning, and emergency operation. 2. Determine operating window. Gather all relevant process data for each operating case, including fluid data, fluid name, phase, physical properties, special aspects like corrosiveness, toxicity, etc., and operating data, flow rate, pressure, temperature, density, and viscosity. Consider application aspects such as continuous batch operation, pulsating flow, unidirectional or bidirectional flow, backflow risk, mechanical integrity, vibration, and hydraulic noise. 3. Collect environmental data. Include aspects like accessibility, physical location relative to equipment and piping, mechanical integrity, electrical safety, health, safety, and environmental conditions, and requirements of the plant organization, maintenance, data collection, self-diagnostic features, etc. Ensure compliance with local and international regulations and certifications. 4. Select adjusted range and accuracy. Ensure the selected range and accuracy meet the process requirements. 5. Select measurement options. Gather additional data required for the selected measurement principle. 6. Select suitable instrument types. Choose suitable makes and types from the approved vendors list, considering the types of instruments already installed at the principal's site to control variety. 7. Evaluate measurement options. Assess the pros and cons of each option, considering process condition coverage, performance, compliance with environmental and organizational aspects, total cost of ownership over 10 years, additional hardware requirements, and specific maintenance aspects. Specific instrument requirements. Instruments should use SI units unless otherwise specified. Instruments must have defined ranges and spans, ensuring they cover the operating window with appropriate accuracy. Signal transmission can be electric or pneumatic, with specific protocols recommended. Power supply should be determined based on the criticality of the application, with options for uninterruptible power supply. For electrical safety in explosive atmospheres, appropriate protective measures must be taken, including selecting the type of protection based on hazardous area classification. All instruments, junction boxes, cabinets, panels, and ancillary equipment must have nameplates indicating the tag number and service. Measurement accuracy should be defined based on the duty and service, with different tolerance classes for various applications, custody transfer, monitoring, control, etc. Requirements for material inspection, certification, and marking of instruments should be followed, especially for inline and online instruments. Instruments should have test facilities for indication lamps to allow easy testing. Environmental protections. Instruments should comply with the environmental conditions specified in the project specification. Plant-mounted instruments should be suitable for industrial, humid, saliferous, and corrosive atmospheres, with adequate protection based on the electrical area classification. For outdoor locations, instruments should meet the climatic conditions of the relevant location class and have a minimum protection degree. Instruments and related components should be protected against mechanical and corrosive influences, with special requirements for tropical, marine, and offshore environments. Electromagnetic compatibility, EMC. Instruments should comply with the latest EMC policies, and metal cable glands should be used for instrument signal cables with proper earthing connections. Plant instruments. General guidelines. Instruments with 4 to 20 milliamps output signals are preferred over discrete, direct-mounted field switches. Instruments should be finished in standard colors, avoiding red or yellow unless specified for specific services. The upper and lower pressure and temperature limits of pressure-containing parts should meet the requirements of the piping class or related equipment design. Selection of materials. Materials should be corrosion-resistant and suitable for the process conditions. For wetted parts of inline instruments, materials should meet the minimum requirements of the piping class. Special material requirements apply for sour or wet H2S services, hydrogen fluoride alkylation services, chemical plants, and services with strong reducing acids. Instruments in oxygen service should meet specific requirements for oxygen handling. Diaphragm seals. Diaphragm seals may be used for instruments in specific applications, such as viscous or high-temperature fluids. The seals should be of welded construction, and the complete assembly should be ordered as an integral part of the instrument. The length of capillary tubing should suit the application, with specific requirements for thermal insulation and tracing in certain environments. Accessibility levels. Accessibility levels for instruments are defined to ensure safe and easy access for operational attention and maintenance. Instruments should be installed considering their location and accessibility, avoiding excessive vibration and ensuring proper representative measurements. Protective shades may be used in tropical and subtropical areas to protect instruments from sun radiation and rain. Local panels and cubicles. Local panels should be avoided unless approved, and materials and paint systems should be suitable for the intended location. Instruments and local panels should be mounted at eye level and protected from steam outlets and water. Installation notes. Inline instruments should be installed by the mechanical engineering discipline under the supervision of the instrument engineering discipline. Plant instruments. General instruments with 4 to 20 mA output signals are preferred to discrete, direct-mounted field switches due to their lower failure rates, better accuracy, and improved stability. This preference allows for instrument signal analysis and measurement comparison. Discrete, direct-mounted field switches should not be used unless specified or approved by the principal. IPF trip initiators of SIL 1 and higher should have a red color, and the finish of plant-mounted instruments in oxygen service should be yellow. The finish of all other plant-mounted instruments may be in the manufacturer's standard color, but not red or yellow. Inline instruments must comply with the requirements of the piping class or equipment in or on which the instruments are installed. Integral and receiving indicators. Integral or receiving indicators should be considered as an alternative to pressure and temperature gauges. Where a local indicator is required to support operating personnel, the physical location of the indicator should be selected so that it can be read from the intended operator position. If this requirement cannot be met by an integral indicator, a receiving indicator shall be applied. Integral and receiving indicators required for operational reasons shall be shown on PEFs and shall present measurement information in engineering units. Blind transmitters are preferred for all applications where an integral indicator is not required for operational reasons. Some transmitter designs are only available with an integral indicator. Such an indicator is acceptable, and where local indication is not a requirement, these indicators shall not be shown on PEFs, and no size, display/location requirements apply. Pressure and temperature limits of pressure-containing parts. For inline instruments, the upper and lower pressure and temperature limits of the pressure-containing parts shall meet at least the requirements of the piping class. For inline instruments associated with equipment where no piping class applies, the upper and lower pressure and temperature limits of the pressure-containing parts shall meet at least the upper and lower design pressure and temperature of the related equipment. For online instruments, the upper and lower pressure limits of the pressure-containing parts shall meet at least the requirements of the piping class. For online instruments associated with equipment where no piping class applies, the upper and lower pressure limits of pressure-containing parts shall meet at least the upper and lower design pressure of the equipment. In addition, differential pressure type instruments shall be capable of withstanding the upper and lower pressure limit requirements of the piping class in either direction, positive and negative. Selection of materials. The selection of materials shall be based on the process conditions, and the selected materials shall be corrosion resistant. The material selection is in general related to the material of the equipment and piping. As a general rule, AISI 36L will be suitable in systems with austenitic stainless steel or carbon steel equipment and piping, but 36L stainless steel may be unsuitable in carbon steel systems containing water with chlorides. The stainless steel shall be resistant to intergranular corrosion as per ASTM A262 Practice E. Specific materials selection requirements apply to the following categories. Sour or wet H2S service. The materials selection of parts of instruments and components which under any process condition are in contact with process water or aqueous condensate shall comply with the relevant standards for sour service. Hydrogen fluoride HF. Alkylation service. The material selection for wetted parts of instruments and components shall comply with the requirements for HF service. Chemical plants, AISI 3/6L, is generally suitable for systems with stainless steel and carbon steel equipment and piping. For special stainless steels with increased MO content, Incolloy 825 and or Hastalloy C276 should be used for pressure transmitters and related components. Services with strong reducing acids. For services where strong reducing acids such as pure hydrochloric and sulfuric acid are used, all wetted parts, excluding the diaphragms of pressure transmitters and diaphragm seals, shall be of Hastalloy B2, and the measuring element diaphragm material shall be tantalum. Oxygen service. All instrumentation in oxygen service shall meet the specific requirements for oxygen service. The measuring element diaphragm material shall be selected in accordance with these requirements. Diaphragm seals instruments may be provided with integral or remote diaphragm seals. Diaphragm seals are typically employed in applications with viscous, waxy, sticky, or plugging surfaces, or when fluid temperature exceeds the maximum allowable temperature of the sensing element. The diaphragm seal size shall be selected to obtain the required instrument accuracy. Diaphragm seals shall be ordered as an integral part of the instrument, and the complete diaphragm seal assembly shall be of welded construction. For instruments with remote seals, the capillary material shall be stainless steel AISI 360L and shall be mechanically protected by flexible stainless steel armoring. The length of the capillary tubing shall suit the application, but shall be at least 1 meter. If capillary tubing is exposed to direct sun radiation or extreme temperature fluctuations, thermal insulation and tracing should be considered. Accessibility levels. Accessibility levels identify the effort required to reach devices such as instruments, measuring elements, instrument process connections, and block valves for operational attention or regular maintenance. 4 accessibility levels are defined. Permanent accessibility. Devices are permanently accessible if located not more than 0.5 meters horizontally away and not more than 1.7 meters vertically above grade, platform, or walkway, with no obstructions and safely reachable during plant operation. Limited accessibility. Devices have limited accessibility if located not more than 1 meter horizontally away and at a height between 1.7 and 4 meters above grade, platform, or walkway, with no obstructions and safely reachable by mobile platform or ladder. Poor accessibility. Devices have poor accessibility if located more than 4 meters above grade, platform, or walkway, or at any location requiring temporary facilities for safe access. Inaccessibility. Devices are inaccessible if they cannot be safely reached during plant operation for operational attention and maintenance. Location and accessibility. Field-mounted instruments shall be installed considering their location and accessibility, avoiding excessive vibration and ensuring representative measurements. Limited accessibility is acceptable for indicating instruments if they can be properly read from a permanently accessible location. Heavy equipment should be accessible by mobile hoisting equipment or have permanent hoisting facilities if necessary. Instruments and their impulse lines should have sufficient free space for maintenance activities. Protective shades. In tropical and subtropical areas, electronic instruments exposed to direct sun radiation should have protective shades to limit temperature variations and reduce zero-span shifts. Shades might also serve as umbrellas to protect instruments from condensation during heavy rains. Local panels and cubicles. Local panels should be avoided unless approved and must be made of materials and paint systems suitable for the intended location. Instruments in local panels should be mounted at eye level, protected from steam outlets and water. Process fluids should not have direct connections with enclosed instrument panels. General installation notes. Inline instruments such as inline flow meters, control valves, orifice plates, strainers, and heavy offline equipment, such as displacer-level instruments and tank gauges, should be installed by the mechanical engineering discipline under the supervision of the instrument engineering discipline. Flow instruments. General flow instruments are critical for measuring and controlling the flow of various fluids in the plant. They must be selected based on the specific process requirements and environmental conditions. The selection process should ensure accuracy, reliability, and compatibility with the system. Vortex flow meters. Vortex flow meters measure the flow rate by detecting the vortices shed by a bluff body placed in the flow stream. They are suitable for measuring the flow of liquids, gases, and steam. Applications. Vortex flow meters are used in a variety of applications, including steam flow measurement, process control, and energy management. Advantages. These meters have no moving parts, which minimizes maintenance requirements. They provide accurate and repeatable measurements over a wide range of flow rates and are capable of handling high temperatures and pressures. Limitations. Vortex meters may not perform well in low flow conditions and can be affected by vibration and pulsating flows. Ultrasonic flow meters. Ultrasonic flow meters use sound waves to measure the flow rate of a fluid. There are two main types, transit time and Doppler. Transit time meters measure the time difference between ultrasonic pulses transmitted with and against the flow, suitable for clean fluids. Doppler meters measure the frequency shift of an ultrasonic signal reflected by particles or bubbles in the fluid, suitable for dirty or aerated fluids. Applications. Ultrasonic flow meters are used in water and wastewater treatment, chemical processing, and oil and gas industries. Advantages. These meters are non-intrusive, have no moving parts, and can be installed without shutting down the process. They provide accurate measurements over a wide range of flow rates and are suitable for large pipe diameters. Limitations. The performance of ultrasonic meters can be affected by the presence of air bubbles, solid particles, and the condition of the pipe's inner surface. Electromagnetic flow meters. Electromagnetic flow meters, also known as mag meters, measure flow based on Faraday's law of electromagnetic induction. They are suitable for measuring the flow of conductive liquids. Applications. Commonly used in water and wastewater treatment, chemical processing, and food and beverage industries. Advantages. Mag meters have no moving parts, providing long-term reliability and minimal maintenance. They are highly accurate and can measure both high and low flow rates. They are unaffected by temperature, pressure, and viscosity changes. Limitations. Electromagnetic flow meters can only measure the flow of conductive fluids. They require a power supply and can be affected by electrical noise. Coriolis mass flow meters. Coriolis mass flow meters measure the mass flow rate of a fluid by detecting the Coriolis effect. They are suitable for a wide range of fluids, including liquids, gases, and slurries. Applications. Used in chemical processing, oil and gas, food and beverage, and pharmaceutical industries. Advantages. Coriolis meters provide direct mass flow measurement, which is highly accurate and independent of fluid properties such as density, temperature, and viscosity. They have no moving parts, which reduces maintenance requirements. Limitations. These meters can be expensive and may have a higher pressure drop compared to other types of flow meters. They are also sensitive to external vibrations and require careful installation. Thermal dispersion mass flow meters. Thermal dispersion mass flow meters measure the mass flow rate of gases based on the principle of heat transfer. They are suitable for clean gases and can be used in various industrial applications. Applications. Commonly used in HVAC systems, compressed air systems, and process gas monitoring. Advantages. These meters provide direct mass flow measurement with no need for temperature and pressure compensation. They have no moving parts, which minimizes maintenance. They can measure very low flow rates and have a wide turn-down ratio. Limitations. Thermal dispersion meters are sensitive to changes in gas composition and may require calibration for different gas mixtures. They are not suitable for measuring the flow of liquids or dirty gases. Differential pressure type flow meters. Differential pressure deep flow meters measure the flow rate by detecting the pressure drop across a restriction in the flow path, such as an orifice plate, venturi tube, or flow nozzle. Applications. Used in various industries including oil and gas, chemical processing, and water treatment for measuring the flow of liquids, gases, and steam. Advantages. DP flow meters are versatile and can be used for a wide range of fluids. They are reliable, have a long history of use, and can be installed in large pipelines. Limitations. These meters can introduce a significant pressure drop in the system, which may not be desirable. They require regular maintenance and calibration to ensure accuracy. DP meters can be affected by changes in fluid density, temperature, and pressure. Variable area flow meters. Variable area flow meters, also known as rotameters, measure the flow rate based on the position of a float within a tapered tube. The flow rate is indicated by the height of the float. Applications. Commonly used in laboratories, chemical processing, and water treatment for measuring the flow of liquids and gases. Advantages. Simple and cost-effective, with no external power required. They provide a direct visual indication of flow rate and are easy to install and maintain. Limitations. Variable area flow meters are generally less accurate than other types and are limited to smaller pipe sizes. They are affected by changes in fluid density and viscosity. Turbine meters measure the flow rate by detecting the rotational speed of a turbine placed in the flow stream. The rotational speed is proportional to the flow rate. Applications. Used in the oil and gas industry, water distribution, and chemical processing for measuring the flow of clean liquids and gases. Advantages. Turbine meters provide high accuracy and a wide range of flow rates. They have good repeatability and a fast response time. Limitations. These meters have moving parts that can wear over time and may require regular maintenance. They are sensitive to changes in fluid properties and can be affected by particulate matter in the flow. Positive displacement meters. Positive displacement (PD) meters measure the flow rate by capturing a fixed volume of fluid and counting the number of times the volume is filled. Types include gear meters, piston meters, and diaphragm meters. Applications. Commonly used in the water industry, fuel dispensing, and chemical processing for measuring the flow of viscous and non-viscous fluids. Advantages. PD meters provide high accuracy and can measure very low flow rates. They are not affected by changes in fluid properties such as density and viscosity. Limitations. These meters have moving parts that can wear and require regular maintenance. They are generally limited to smaller pipe sizes and can introduce a pressure drop in the system. Flow meter accessories. Flow meter accessories include items such as flow conditioners, strainers, and signal converters that enhance the performance and functionality of the primary flow measurement device. Flow conditioners. Used to create a uniform flow profile and reduce disturbances that can affect the accuracy of flow measurements. Strainers. Installed upstream of the flow meter to remove debris and particulate matter that can damage the meter or affect its accuracy. Signal converters. Convert the raw signal from the flow meter into a standardized output that can be used for process control and monitoring. Meter proving facilities. Meter proving facilities are used to calibrate and verify the accuracy of flow meters. This involves comparing the flow meter's readings with a known reference standard. Applications. Used in industries where precise flow measurements are critical, such as oil and gas, chemical processing, and water treatment. Advantages. Ensures the accuracy and reliability of flow measurements, which is essential for process control and regulatory compliance. Limitations. Meter proving can be time-consuming and requires specialized equipment and trained personnel. Regular calibration is necessary to maintain accuracy over time. Level instruments. General level instruments are essential for measuring the level of liquids and solids in tanks, vessels, and other containers. The selection of level instruments should be based on the specific process requirements, fluid properties, and environmental conditions. Selection of level instruments. Selecting the appropriate level instrument involves considering various factors such as the type of fluid, liquid, solid, slurry, the physical properties of the fluid, density, viscosity, dielectric constant, the process conditions, temperature, pressure, and the installation requirements. Applications. Level instruments are used in various industries including oil and gas, chemical processing, food and beverage treatment for measuring the level of liquids, solids, and slurries. Advantages. Properly selected level instruments ensure accurate and reliable level measurement, which is critical for process control, safety, and inventory management. Limitations. The performance of level instruments can be affected by factors such as turbulence, foam, vapor, and buildup on the measuring element. Differential pressure level instruments. Differential pressure (DP) level instruments measure the level of a fluid by detecting the pressure difference between 2 points, typically the bottom and top of the tank or vessel. Applications. Used in various industries for measuring the level of liquids in pressurized and non-pressurized vessels, including storage tanks and process vessels. Advantages. DP level instruments are versatile and can be used for a wide range of fluids. They are reliable and have a long history of use. They can be used for continuous level measurement and are suitable for high pressure and high temperature applications. Limitations. These instruments can be affected by changes in fluid density, temperature, and pressure. Regular calibration and maintenance are required to ensure accuracy. They may not be suitable for measuring the level of solids or slurries. Displacer level instruments. Displacer level instruments measure the level based on the principle of buoyancy. A displacer element is suspended in the fluid, and the buoyant force acting on the displacer changes with the fluid level. Applications. Commonly used in the oil and gas industry, chemical processing, and water treatment for measuring the level of liquids in tanks and vessels. Advantages. Displacer level instruments provide accurate and reliable level measurement for a wide range of liquids. They are suitable for high pressure and high temperature applications and can be used for continuous level measurement. Limitations. These instruments have moving parts that can wear over time and require regular maintenance. They may not be suitable for measuring the level of solids or slurries and can be affected by changes in fluid density. Level instruments. Capacitance level probes. Capacitance level probes measure the level of a fluid based on changes in capacitance between the probe and the tank wall. The capacitance varies with the level of the dielectric fluid. Applications. Used in various industries for measuring the level of liquids and solids, including water treatment, chemical processing, and food and beverage industries. Advantages. Capacitance probes are versatile and can be used for a wide range of fluids, including liquids, solids, and slurries. They provide accurate and reliable measurements and are suitable for high temperature and high pressure applications. They have no moving parts, which minimizes maintenance. Limitations. The performance of capacitance probes can be affected by changes in the dielectric constant of the fluid, buildup on the probe, and variations in temperature and pressure. Proper calibration and maintenance are required to ensure accuracy. Radar-type instruments. Radar-type instruments use microwave radar signals to measure the level of a fluid. The radar signals are transmitted from the instrument and reflected back from the fluid surface. The time delay between the transmitted and reflected signals is used to calculate the level. Applications. Commonly used in the oil and gas industry, chemical processing, and water treatment for measuring the level of liquids and solids in tanks and vessels. Advantages. Radar instruments provide accurate and reliable level measurements, regardless of the fluid's properties. They are suitable for high temperature and high pressure applications and can measure the level of both liquids and solids. They have no moving parts, which minimizes maintenance. Limitations. Radar instruments can be affected by obstructions in the tank, turbulence, foam, and vapor. They require proper installation and calibration to ensure accuracy. Level switches. Level switches provide discrete on-off level indication and are used to detect high and low levels in tanks and vessels. Various types of level switches are available, including float switches, capacitance switches, and vibrating fork switches. Applications. Used in various industries for overfill protection, pump control, and alarm signaling. Common applications include water treatment, chemical processing, and food and beverage industries. Advantages. Level switches are simple, reliable, and cost-effective. They are easy to install and maintain and provide a clear indication of high or low levels. They are suitable for a wide range of fluids, including liquids and solids. Limitations. Level switches provide only discrete level indication and cannot be used for continuous level measurement. They may have moving parts that can wear over time and require regular maintenance. The performance of some types of level switches can be affected by changes in fluid properties, such as viscosity and density. Tank gauging systems for product and storage tanks. Tank gauging systems provide continuous level measurement for inventory management and process control in product and storage tanks. These systems typically include level sensors, temperature sensors, and data acquisition systems. Applications. Commonly used in the oil and gas industry, chemical processing, and water treatment for measuring the level of liquids in large storage tanks and process vessels. Advantages. Tank gauging systems provide accurate and reliable level measurements, which are essential for inventory management and process control. They can measure the level of various fluids, including crude oil, refined products, chemicals, and water. These systems often include temperature compensation to improve accuracy. Limitations. Tank gauging systems can be complex and expensive. They require proper installation, calibration, and maintenance to ensure accuracy. The performance of some systems can be affected by tank obstructions, turbulence, and vapor. Pressure instruments. Pressure gauges are essential for measuring and indicating the pressure of gases and liquids in various industrial applications. They provide a visual indication of pressure within a system and are critical for monitoring and maintaining safe operating conditions. Applications. Pressure gauges are used in a wide range of industries, including oil and gas, chemical processing, water treatment, and HVAC systems. They are commonly used to monitor process pressure, check for leaks, and ensure safe operating conditions. Advantages. Pressure gauges are simple to use, provide immediate visual feedback, and are available in various ranges and configurations to suit different applications. They are generally cost-effective and require minimal maintenance. Limitations. The accuracy of pressure gauges can be affected by factors such as temperature, vibration, and mechanical damage. Regular calibration and maintenance are required to ensure reliable readings. They are also limited to providing local rather than remote indication. Other pressure instruments. Other pressure instruments include a variety of devices designed to measure and control pressure in different applications. These instruments offer more advanced features and capabilities compared to traditional pressure gauges. Pressure transmitters. Pressure transmitters convert pressure measurements into an electrical signal that can be transmitted to a control system. They provide continuous, remote monitoring of pressure and are used in various industries for process control and automation. Advantages. Pressure transmitters provide accurate and reliable pressure measurements, can be integrated with control systems for real-time monitoring, and offer advanced features such as digital communication and diagnostics. Limitations. They are more complex and expensive than pressure gauges, require a power supply, and may need regular calibration and maintenance. Pressure switches. Pressure switches are devices that activate or deactivate a circuit when a certain pressure level is reached. They are used for safety and control applications, such as activating alarms or shutting down equipment when pressure limits are exceeded. Advantages. Pressure switches are simple, reliable, and provide an automatic response to pressure changes. They are available in various configurations to suit different applications. Limitations. Pressure switches provide discrete, on-off control rather than continuous measurement. They may have moving parts that can wear over time and require regular maintenance. Differential pressure transmitters. These instruments measure the difference in pressure between 2 points in a system. They are commonly used for flow measurement, level measurement in pressurized vessels, and filter monitoring. Advantages. Differential pressure transmitters provide accurate and reliable measurements of pressure differences, can be integrated with control systems, and offer advanced features such as digital communication and diagnostics. Limitations. They are more complex and expensive than single-point pressure instruments, require a power supply, and may need regular calibration and maintenance. Pressure recorders. Pressure recorders are used to continuously record pressure measurements over time. They can be mechanical or electronic and are used in applications where a historical record of pressure data is required. Advantages. Pressure recorders provide a continuous record of pressure measurements, which is useful for trend analysis and troubleshooting. They are available in various configurations to suit different applications. Limitations. Mechanical recorders may require regular maintenance and calibration. Electronic recorders require a power supply and may need regular calibration and maintenance. Manometers are devices that measure pressure using a column of liquid. They are simple, accurate, and are used for low-pressure measurements. Advantages. Manometers provide accurate and direct pressure measurements, are simple to use, and require no power supply. They are cost-effective for low-pressure applications. Limitations. Manometers are limited to low-pressure applications, are not suitable for high-pressure or dynamic pressure measurements, and require careful handling to avoid liquid spillage and contamination. Temperature instruments. General temperature instruments are essential for measuring and monitoring the temperature of processes and equipment in various industrial applications. Accurate temperature measurement is critical for process control, safety, and quality assurance. Dial thermometers. Dial thermometers measure temperature using a bimetallic strip or a gas mercury-filled bulb that expands or contracts with temperature changes, causing a needle to move on a dial. Applications, commonly used in HVAC systems, industrial processes, and laboratory environments for local temperature indication. Advantages. Dial thermometers are simple, durable, and easy to read. They do not require a power supply and are relatively inexpensive. Limitations. They provide only local indication and are less accurate than electronic temperature sensors. They may require regular calibration and are not suitable for remote monitoring. Thermocouples. Thermocouples measure temperature based on the voltage generated at the junction of two dissimilar metals. The voltage is proportional to the temperature difference between the junction and a reference point. Applications. Widely used in industrial processes, furnaces, and engines for temperature measurement over a wide range of temperatures. Advantages. Thermocouples are robust, have a wide temperature range, and provide fast response times. They are relatively inexpensive and can be used in harsh environments. Limitations. Thermocouples require a reference junction and can be affected by electromagnetic interference. They are less accurate than resistance temperature detectors, RTDs, and require regular calibration. Resistance thermometers, RTDs. Resistance thermometers, or RTDs, measure temperature based on the change in electrical resistance of a metal, typically platinum, with temperature. Applications, used in industrial processes, HV systems, and laboratory environments for accurate and stable temperature measurement. Advantages. RTDs provide accurate and repeatable temperature measurements over a moderate temperature range. They are stable and have a long lifespan. Limitations. RTDs are more expensive than thermocouples and have a slower response time. They require a power supply and can be affected by lead wire resistance. Instruments for thermocouple and resistance thermometers. Various instruments are used to read and interpret the signals from thermocouples and RTDs, including temperature transmitters, controllers, and data acquisition systems. Temperature transmitters convert the signal from a thermocouple or RTD into a standardized output, e.g. 420 mA, for transmission to a control system. Advantages: provide accurate and reliable temperature measurement, can be integrated with control systems, and offer advanced features such as digital communication and diagnostics. Limitations: more complex and expensive than standalone sensors, require a power supply, and may need regular calibration and maintenance. Used to maintain a process at a desired temperature by comparing the measured temperature with a set point and controlling a heating or cooling element. Advantages: provide precise temperature control, can be integrated with other control systems, and are available in various configurations to suit different applications. Limitations: more complex and expensive than basic temperature sensors, require a power supply, and may need regular calibration and maintenance. Data acquisition systems record temperature measurements from multiple sensors for monitoring, analysis, and process control. Advantages: provide comprehensive temperature monitoring, can store historical data for analysis, and are suitable for complex processes with multiple measurement points. Limitations: more expensive and complex than standalone sensors, require a power supply, and may need regular maintenance and calibration. Electrical parameters. General electrical parameters instruments are essential for measuring and monitoring electrical characteristics such as voltage, current, resistance, and power in various industrial applications. Accurate measurement of electrical parameters is critical for process control, safety, and equipment performance. Voltage measurement instruments. Instruments used for measuring voltage include voltmeters, voltage transducers, and potential transformers. Applications: used in power distribution, electrical equipment testing, and industrial process control to measure voltage levels. Advantages: provide accurate voltage measurements, which are essential for maintaining equipment performance and safety, available in various configurations for different applications. Limitations: some instruments require a power supply and regular calibration. They can be affected by electromagnetic interference. Current measurement instruments. Instruments used for measuring current include ammeters, current transformers, and current transducers. Applications: used in power distribution, electrical equipment testing, and industrial process control to measure current flow. Advantages: provide accurate current measurements, which are essential for monitoring and controlling electrical systems. Available in various configurations for different applications. Limitations: some instruments require a power supply and regular calibration. They can be affected by electromagnetic interference. Resistance measurement instruments. Instruments used for measuring resistance include ohmmeters and resistance bridges. Applications: used in electrical equipment testing, maintenance, and industrial process control to measure electrical resistance. Advantages: provide accurate resistance measurements, which are essential for assessing the condition of electrical components and systems, available in various configurations for different applications. Limitations: some instruments require a power supply and regular calibration. They can be affected by temperature changes and other environmental factors. Power measurement instruments. Instruments used for measuring power include wattmeters, power analyzers, and energy meters. Applications: used in power distribution, electrical equipment testing, and industrial process control to measure electrical power consumption and performance. Advantages: provide accurate power measurements, which are essential for monitoring and optimizing energy usage, available in various configurations for different applications. Limitations: some instruments require a power supply and regular calibration. They can be affected by electromagnetic interference and other environmental factors. Speed instruments. General speed instruments are essential for measuring the rotational speed of machinery and equipment in various industrial applications. Accurate speed measurement is critical for process control, safety, and equipment performance. Tachometers. Tachometers measure the rotational speed of a shaft or disc, typically in revolutions per minute, RPM. They can be mechanical, electronic, or optical. Applications used in industrial processes, automotive testing, and machinery maintenance to measure the speed of motors, engines, and other rotating equipment. Advantages provide accurate and immediate speed measurements, available in various configurations, including handheld and panel-mounted models. Limitations. Some tachometers require a power supply and regular calibration. Mechanical tachometers can wear over time and may require maintenance. Stroboscopes. Stroboscopes measure the speed of rotating or oscillating objects by emitting flashes of light at adjustable frequencies. The speed is determined by matching the flash frequency to the object's motion. Applications. Used in industrial processes, machinery maintenance, and quality control to measure the speed of rotating equipment and inspect moving parts. Advantages. Provide accurate and non-contact speed measurements. Can be used to inspect moving parts for defects and wear. Limitations. Stroboscopes require a power supply and may need regular calibration. They can be affected by ambient light conditions. Speed transducers. Speed transducers convert mechanical speed into an electrical signal that can be monitored and recorded by control systems. Applications. Used in industrial processes, automotive testing, and machinery maintenance to measure and monitor the speed of motors, engines, and other rotating equipment. Advantages. Provide continuous and remote speed measurement. Can be integrated with control systems for real-time monitoring and process control. Limitations. Speed transducers require a power supply and regular calibration. They can be affected by electromagnetic interference and other environmental factors. Machine monitoring. General machine monitoring instruments are essential for assessing the condition and performance of machinery and equipment in various industrial applications. These instruments help in detecting potential issues early, ensuring optimal operation and preventing costly breakdowns. Vibration monitors. Vibration monitors measure the vibration levels of machinery to detect imbalances, misalignments, and other mechanical issues. Applications. Used in industries such as oil and gas, power generation, and manufacturing for monitoring rotating equipment like pumps, motors, and turbines. Advantages. Provide early detection of mechanical issues, helping to prevent equipment failures and extend machinery life. They can be used for continuous monitoring and integrated with control systems. Limitations. Vibration monitors can be sensitive to external noise and require proper installation and calibration. Regular maintenance is needed to ensure accuracy. Bearing monitors. Bearing monitors measure the condition of bearings in machinery, identifying wear and potential failure points. Applications. Commonly used in manufacturing, power generation, and automotive industries to monitor bearings in motors, pumps, and other rotating equipment. Advantages. Early detection of bearing issues helps prevent catastrophic failures and reduces maintenance costs. They provide continuous monitoring and can be integrated with control systems. Limitations. Bearing monitors require regular calibration and maintenance. They can be affected by external factors such as temperature and load variations. Temperature monitors. Temperature monitors measure the operating temperature of machinery and equipment to detect overheating and ensure optimal performance. Applications. Used in various industries to monitor motors, generators, compressors, and other equipment. Advantages. Provide continuous temperature monitoring, which is critical for preventing overheating and equipment damage. They can be integrated with control systems for real-time alerts. Limitations. Temperature monitors require proper installation and calibration. They can be affected by environmental conditions and may need regular maintenance. Lubrication monitors. Lubrication monitors measure the condition and levels of lubricants in machinery to ensure proper lubrication and prevent wear. Applications. Commonly used in manufacturing, automotive, and heavy machinery industries to monitor lubrication in engines, gearboxes, and bearings. Advantages. Ensure optimal lubrication, reducing wear and extending the life of machinery. They provide continuous monitoring and can alert operators to lubrication issues. Limitations. Lubrication monitors require regular maintenance and calibration. They can be affected by contamination and require proper installation. Flame detection. General flame detection instruments are essential for ensuring safety in environments where flammable gases or liquids are present. They detect the presence of flames and provide early warning to prevent fires and explosions. UV-IR flame detectors. UV-IR flame detectors use ultraviolet UV and infrared IR sensors to detect the presence of flames by sensing the specific wavelengths of light emitted by a flame. Applications. Used in oil and gas facilities, chemical plants, and industrial manufacturing for early fire detection. Advantages. Provide fast and accurate flame detection with a low rate of false alarms. They can detect flames through smoke, dust, and vapors. Limitations. UV-IR flame detectors require a clear line of sight to the flame and can be affected by environmental factors such as sunlight and hot surfaces. Multispectrum flame detectors. Multispectrum flame detectors use multiple IR sensors to detect flames over a broad spectrum of wavelengths, providing enhanced detection capabilities. Applications. Commonly used in high-risk environments such as refineries, petrochemical plants, and aerospace facilities. Advantages. Offer high sensitivity and fast response times with a low rate of false alarms. They can detect flames through smoke, dust, and vapors, and are effective in challenging environments. Limitations. Multispectrum flame detectors can be expensive and require regular maintenance and calibration. They need a clear line of sight to the flame. Infrared flame detectors. Infrared IR flame detectors use IR sensors to detect the specific wavelengths of light emitted by a flame. Applications. Used in a variety of industries, including oil and gas, chemical processing, and manufacturing for fire detection. Advantages. Provide fast and accurate flame detection with a low rate of false alarms. They can detect flames through smoke and dust. Limitations. IR flame detectors require a clear line of sight to the flame and can be affected by environmental factors such as hot surfaces and sunlight. Regular maintenance and calibration are necessary. Optical flame detectors. Optical flame detectors use sensors to detect the light emitted by a flame. They can include UV, IR, or visible light sensors. Applications. Commonly used in industrial settings, refineries, and chemical plants for fire detection. Advantages. Provide fast and accurate flame detection with a low rate of false alarms. They can detect flames through smoke and dust. Limitations. Optical flame detectors require a clear line of sight to the flame and can be affected by environmental factors such as sunlight and hot surfaces. Regular maintenance and calibration are necessary.